Channels, and of course also natural rivers, are not always prismatic. They can present progressive widening and narrowing, as illustrated here, for example, with the gate of this dam aimed at regulating the water level and the navigation lock that allows the vessels to navigate through this system. If we assume a wide rectangular cross-section, as we already know, the hydraulic radius can be approximated by the water depth. This simplification will be useful to analyze the evolution of the parameters of the flow when the width of the channel changes. For example, if we consider a progressive narrowing as sketched here, where the width reduces from L1 to L2, we can analyze the evolution of the specific energy. The general expression is recalled here, and adapted to the case of a wide rectangular cross-section in the third column of the table. With this expression, it is easy to see that if the width L reduces, the specific energy for a given depth will increase. This is valid for any water depth h, in such a way that the specific energy curve corresponding to the narrow channel L2 is everywhere above the specific energy curve corresponding to the width L1. Looking at the equation of the critical depth, we see that Hc also increases when the width decreases. So C2 is at the right of C1 and of course above C1 and corresponds to a critical depth Hc2 larger than Hc1. We can draw the same conclusion for the normal depth. HU2, corresponding to L2, is larger than HU1. So, when the channel width decreases, the normal and critical depths increase. The analysis was illustrated here for a mild slope channel, but it is also valid for steep slope channels. With this information in mind, we will now analyze the water profile in this progressively narrowing channel considering a mild bed slope. The first step is to identify the normal and critical depth. We can link the specific energy diagram to the water depth in the representation of the water profile on the right side using the 45-degree line as illustrated. Remember, we have the depth here, so Hc1 here also, that we can translate to this representation of the water profile. The critical depths Hc1 and Hc2 are indicated here and here, and in the transition, we can just represent the progressive increase of the critical depth, as this depth can be calculated locally for any cross-section, even in the case of non-prismatic channels. Contrarily to the critical depth, the normal depth can only be represented in prismatic channels, and not in the transition, because the uniform flow does not exist in non-prismatic channels. So, we have the two green lines here representing the uniform flow, but nothing in the transition. In the specific energy diagram, we have indicated with red arrows the possible evolution of the specific energy depending on the water depth. We will assume a uniform flow far upstream here and far downstream from the transition. Now, taking a closer look at the specific energy diagram, we can indicate our starting point A, corresponding to the normal depth HU1, and the arrival point B, corresponding to the normal depth HU2. To reach point B, starting from point A, we will follow this arrow, which means that the flow increases its specific energy until a point 1 that will be at a slightly higher energy level than the final goal at point B, in order to keep some energy for the transition between the wide section and the narrow section that is between point 1 and point B. From this point 1, the flow crosses the transition by losing some energy and thus some specific energy and reaches point B. This head loss in the transition explains why a higher specific energy was required at point A. We can now translate this evolution into an evolution of the water depth, and in this way into a water profile. Starting from the uniform flow U1, the increase in specific energy corresponds to an increase of the water depth through a M1 profile until point 1. The water depth then decreases in the transition to reach U2 corresponding to the uniform flow in the downstream narrow reach. Indeed, as no other water profile tends to the uniform depth in mild slope cases, the only possible water profile is a MU water profile here in the downstream part. This is also clear in the specific energy diagram. No red arrow goes towards U2, they just go away from U2. So the final flow profile is this one. We see that this result is obtained from the specific energy diagram, provided of course that we know the different possible mild slope water profiles. For a practical calculation, the different steps are summarized here. First, we calculate the critical and normal depth, and then represent the flow path on a specific energy diagram. These steps are important, as they allow to know the sequence of water profiles before starting any detailed calculation. For the calculation, as we are in a mild slope channel, and we have assumed a uniform flow far away from the change in width, we will start from downstream. Indeed, as HU is above HC, we have a subcritical flow controlled from downstream. So we calculate and represent the MU profile until point U2. Then, using the Bernoulli equation, we can calculate the flow in the transition. Let us recall the Bernoulli equation. It is written here in equation 1. We will apply this equation between U2 here and point 1. The head losses J1, 2 are detailed in equation 2. We will have to consider the friction losses and local losses, this latter being precisely due to the change in cross-section width. So the local losses are expressed like this, and the head loss coefficient zeta takes the values indicated here. We see that it is more important in the case of a flow deceleration that implies a dispersive flow. Developing all the terms, we obtain equation 3. If we apply this equation to our example, the only unknown is H1, as we know the flow conditions at point U2. Some iterations might be required because H1 appears in different terms. Equation 3 can be solved in one single step if the length delta S of the transition is short, or it can be calculated in several steps, so with many steps of iterations, to increase the accuracy of the results. Finally, after applying the Bernoulli equation to find point 1, we calculate the M1 profile from this point 1, as it is also a downstream controlled water profile. Let us apply this to an example. Consider this channel with a progressive narrowing from 100 meter to 60 meter over a distance delta S of 600 meter. After calculating the normal and critical depths, we represent a specific energy diagram with the two curves corresponding to the two different channel widths. This allows us to identify the water profiles that will develop. In the present case, it will be a M1 profile before the transition, then a decrease of the water depth in the transition until reaching point HU2. So, starting from downstream, we represent the MU profile until point U2. And then, applying the Bernoulli equation, considering the friction head loss but neglecting the local head loss, because we have assumed theta equal to 0, we find a depth at point 1 of 8.16 meter. This evolution can be calculated in one single step over the transition, or for a better accuracy in several steps by dividing the transition into smaller reaches. In the present examples, 5 steps were used. Then from this point 1, we calculate the M1 profile until the abscissa S equal to 0 to obtain the final flow profile illustrated here. In the present example, we see that the flow has not yet reached the upstream normal depth of 5.46 meter. A longer distance would be required therefore, but we know that the M1 profile will anyway tend asymptotically to HU1. The extension to steep slope channels is straightforward. The analysis is conducted exactly using the same procedure. If we consider uniform flows as boundary conditions, we can only have a SU profile in the upstream reach here, and we will have supercritical profiles calculated from upstream. So the SU profile will be followed by an increase of the water depth in the transition, then a S2 profile to reach the normal depth in the downstream reach. Let us now consider a progressive channel widening. We can do the same analysis as the one conducted for a channel narrowing, and conclude in the present case that for a width L2 larger than L1, the specific energy for a given water depth will decrease, as well as the critical and normal depth. This is illustrated here on the specific energy diagram. We have the curve corresponding to L2 that is below the L1 curve. A typical situation is illustrated here, and once again, we will conduct the analysis with the help of the specific energy diagram. Our starting point is at point A, corresponding to the uniform flow U1, and we want to arrive at point B, corresponding to the uniform flow U2. To approach point B, the specific energy has to decrease until a point 1 with a specific energy level slightly higher than point B in order to keep some energy to be lost in the transition. Then, from point 1, the flow crosses the transition until reaching point B that represents the uniform flow U2. The translation of the evolution of the specific energy into water depth is illustrated here. We first have a M2 profile that corresponds to a decrease of specific energy with a decrease in water depth until point 1. Then, the water depth increases in the transition until reaching HU2. The calculation is conducted as follows. First, we determined the critical and normal depths. As we assume a uniform flow far away from the transition, we will have a subcritical flow at the downstream end of the system. So, starting the calculation from downstream, we will represent the MU profile until point U2. Then, using the Bernoulli equation, we calculate the flow through the transition until point 1, in one or several steps, depending of course on the length of the transition and of the required accuracy. And finally, we calculate the M2 profile starting from point 1. It is a downstream control profile, so it is calculated from downstream, and the downstream point is point 1. In all the examples that we have seen until now, the flow remained always subcritical. However, in this illustration, we can identify here a control section in this narrow part. This implies that we have a supercritical flow further downstream. How can such a situation happen? Let us go back to a simple, moderate widening as illustrated here. We can see from the specific energy diagram that the flow can reach the uniform flow U2 by remaining always above the critical depth, even point 1, that is the lowest point of the water profile, it is located above C1. If the width L2 increases, HU2 and HC2 will decrease, and point 1 gets closer to C1. If L2 further increases, point 1 further decreases. And finally, if the process continues, it reaches C1. So if the width L2 becomes even larger, we finally have this situation where the difference in specific energy between U2 and C1 becomes larger than any physically possible head loss in the transition. So let us analyze the evolution of the specific energy in this case. As in the previous cases, we start from point A, representing the uniform flow U1, and we want to reach point B, that represents the uniform flow U2. To approach point B, the specific energy decreases, but it is only possible to decrease until C1, and this is not sufficient to reach point B. Indeed, even if some energy is lost in the transition, we see that it is not sufficient to reach point B. We arrive at a point that is above point B. So, instead of reaching point B directly, the flow depth will decrease in the transition until point 3, which is the only possibility to further decrease the specific energy. This point is below the critical depth HC2, so it will only be possible to reach point B with a hydraulic jump. The specific energy will thus evolve in the downstream wide channel until a point 4 that corresponds to the sequent depth of point B, in such a way that the hydraulic jump can take place between point 4 and the uniform flow in the downstream reach. The hydraulic jump appears as a jump across HC on the specific energy curve, passing from the supercritical left branch of the diagram to the subcritical right branch. The corresponding flow profile from upstream to downstream is illustrated here. Starting from U1, we have a M2 profile until the critical depth at point C1, that is a control section. Then, the water profile crosses the critical depth in a continuous way, and the water depth further decreases in the transition until point 3, below HC2. From point 3, we have a M3 profile until a point 4 here that will be determined as follows. We know that we have a uniform flow at the downstream end. So this implies a MU profile in the downstream reach, because, remember, no mild flow profile tends to the normal depth in the downstream direction. We calculate the sequent curve M3' and find point 4 as the location where M3' intersects MU. This indicates the position of the hydraulic jump. The key steps of the calculation are summarized here. Again, we first calculate HC and HU in both reaches, as usual. From the specific energy diagram, we see that a direct transition to U2 is impossible, so we will have a control section at C1. From this control section, we can calculate the M2 profile in the upstream direction, like this, and the flow in the transition using the Bernoulli equation to find point 3, because we know all the conditions at point C1. Then, from point 3, we can calculate the supercritical profile M3, and finally the position of the hydraulic jump between this M3 profile and the downstream controlled MU profile. Let us apply this procedure to an example. The channel cross-section widens from 40 meter to 100 meter, which is more than the double of the initial width. The discharge Q is 3000 cubic meter per second, and for this value we can calculate the critical and normal depths. The critical depth exists in the widening, which is not the case for the normal depth, because this depth is only defined for prismatic channels. With this information, we can represent the specific energy diagram. We see that the specific energy at U2 is much lower than at C1. So the only possibility is an energy loss with first a M2 profile until a control section C1 that corresponds to the beginning of the transition. Then a decrease of the water depth in the transition, a M3 profile in the downstream part, and then a hydraulic jump to reach U2. So, as we know that there is a control section at C1, this will be the starting point for the calculations. We start with the M2 profile back in the upstream direction, as a M2 profile is a downstream control profile. In this case, it is controlled by the control section. Then, we calculate the flow profile in the transition using Bernoulli's equation to find point 3, considering a head loss coefficient zeta of 0.2 for the widening ridge, and a calculation made here with 5 steps. From there, we can calculate the M3 profile, that is an upstream control profile, and we can also represent the downstream MU profile. Then, by representing the sequent curve M3', we find the position of the hydraulic jump, and we have the final flow profile. So, what have we learned in this lesson? We have analyzed progressive channel narrowing or widening, and we have explained how the specific energy diagram evolves when the channel width changes. We have also explained how to determine the general shape of the water profile in the transition using the specific energy diagram and how to calculate it using the Bernoulli equation. Now it remains to practice all this and to discover some applications of these concepts. So this will be done in the next lesson. Goodbye.